Okay, so I'm going to be recording the rest of this because we're going to be doing some exercises. So this is just what I've been talking about, the different. So the electric motor and the electric generator, it's basically the same principle, just that with one, we have an energy source that's creating a current, and with that current and configuration in the magnetic field, we generate movement. In the generator, we have the same configuration, but we create movement to induce a current and create electrical energy. So it's basically the same principle. And we mentioned, and there are some, these are some examples again. Anything that can have a turbine can do this energy generation. And there are different stages of energy generation. One is the generation, the other is the storage, and the other is the transmission. And so that happens with any sort of electric generation. The tendency right now is to try to create or try to use energy sources that are obviously renewable and clean, right? Under the principle that certain fuels are not going to be renewable. Let's say that air and solar are always going to be there, unless apocalypse or something comes, but they're always going to be there. And so that's the principle, to try to use cleaner energy. It's more difficult to use clean energy. So the turbines that we see here, for example, you can't have those everywhere in the world. There are some places that aren't suitable for that. Solar energy, you can't have that everywhere as well. Other types of energy that generate this, that are being used are these what are called wave breaking energies. So if you have some part in the world where you have a lot of that's near the ocean and there's a lot of waves generate a lot of energy. So if you can have a mechanism where you can take advantage of that sort of wave hitting. And I think there's some of these in here in Baja or in California. That's other ways of generating energy. There's one of those.
No, they should, you know, the bufadora.
Yeah, the bufadora. That's kind of the principle of steam. And so we're going to wrap this up. We're coming back. We already saw this. We talked about inductors, which is basically the representation of a coil. And we were starting to talk about the connections of inductors and how they behave. And I mentioned that this topic is really simple because inductors behave exactly the same way as resistors, because inductors are related to current. We talked about that. Inductors, inductance, coils. I mentioned this more than once, a typical question in the exam. If I have a cable or a wire that has current going through it, the strength of the magnetic field or the force is going to depend on what? On the length of the cable, on the intensity of the current. It's always related to current. So oh yeah. I was going to mention that. Basically, the difference between a resistor and an inductor, in principle, is that the resistor opposes. That's a definition. Opposes the flow of the current. An inductor is going to oppose the direction of the current. So the resistor, if the current is going from A to B or from B to A, the resistor is like the straw. It's just that constriction that's opposing. The inductor is going to react to the current going to one direction and then change it. Because again, magnetism and current have to do with movement. So this is why in the formula, it's related to the derivative of the current, which means the change of the current.
Can you repeat again please, the difference between the resistors and inductors?
Okay, resistors and inductors both have to do with opposition to current.
Okay.
But what's the difference? The resistor is going to oppose the flow of current. Yeah, it's going to make it so, and it doesn't matter where the flow is going. If it's going, again, if you've got the straw and you're pulling on the straw, it doesn't matter if you're pulling on it or you're pushing water back. It's gonna, if you constrict the straw, it's gonna make it difficult. Okay, that's what resistors do. They just oppose the flow. Inductors are going to react to the change in direction of the flow. So it's not just if it's going from A to B, if it suddenly changed from going to B to A. Okay, so what would create that? The current that's coming out of your AC is current that's going positive, negative, positive, negative, positive, negative. Okay, so alternating current, which by the way, I forgot to mention this. I'm going to go back to that, don't worry. This configuration that I just mentioned and all the examples we just gave, by default generate alternating current. By default, the configuration is going to generate positive, it's going to generate a sine wave. We need to convert that to direct current, and again, that's not a topic of this course, but by default, it's a positive, negative, positive, negative. So inductors are going to react to that. They react to the change in current. And that's why we use a differential.
Professor, what does it mean that it says in a series connection when we are daisy? The shape.
Oh,
like
daisy
a
chain, daisy chain. That's just a term in English. A daisy chain, and I don't know where that comes from. A daisy chain is one thing connected. So if you guys were to hold hands, it would be a daisy chain. I don't know why it's called that way. But
Because of the flower, like petals.
I imagine so. It's like one thing connected to the other, and it's called a daisy chain. I think it's Americans more than Europeans, but in English language, there's a lot of terms that are really weird. Daisy chain, piggyback, spitballing. There's a lot of things that like that. So daisy chain just means that. These little chain. Football?
You haven't seen Fresh Musicales?
I do not think so. I would remember.
It's very sweet.
It's very specific. That's very specific.
It's because they sing the song that it's football, football,
Football. I'm gonna look for that. And so inductors in series are going to behave exactly the same way as resistors. What happens with resistors in series? They add up. And you're studying this for the exam. So inductors in series, we're simply going to add them up, and the combined effect of the total inductance is going to be the sum of the inductors. So let's look at a quick. Yes. Yes. Yes.
Oh, okay, so resistors, they dissipate the electrical thing into heat.
They can. That's part of what they do.
And inductors, they turn electrical power into a magnet.
Yeah, the movement is going to generate a magnet. So an inductor is a magnet. So remember that an inductor is a coil is a magnet. And the movement of the current generates a magnet. So automatically an array, if I have, said in a very simple way, if I have 3 inductors with different values, and I want to combine the effect, I can connect the 3 of them. The inductance is going to be the sum. I'm creating a larger magnet.
So inductors are just magnets inside the circuit.
Yeah.
Okay. Okay. Now you get it.
But we're going to see that next semester. It's really not a topic here, but we're also going to see that they have an effect on circuits, not only the magnetism part. They also
They affect the current, obviously.
yeah, and that's also part of it. Okay, while you keep writing, just one thing regarding housekeeping. The solutions to the homework task will be uploaded today. They'll be available today.
I have a question. In the exam, we would just have to do like the equations, right? We don't have to go.
Yeah, in the exam, basically, the spoiler, the problems are going to be, I'm going to put maybe one problem, kind of like the last one in the homework test.
Like
but-
voltage, power.
Yeah, but I'm not gonna ask you to solve the values, I'm gonna ask you to set up the equations.
Okay.
Because
Like
it's,
first one and second one.
yeah, so it wouldn't be really, or I really don't care that you're gonna have to bother with calculating and that. As long as you, yeah, as long as you set up the model correctly, you can use whatever tool you have for that. So what I do want you to review and what I'm gonna upload, more than the values, I need you to compare your analysis procedure and your equations, because there are many places there where we can make a mistake having to do with, depending on how we put the currents and the flow. And so just compare those. If you have any questions, let me know. I don't really care or don't really focus that much on the results, because depending on if you use what software you use to do the solutions, or what conventions you use, those might be a little bit. But yeah, the exam, that's the way it's going to be. Kind of like that, it's going to be a section of theory, like other exams, direct theory, the critical thinking theory, and it's going to be, I think, 1 or 2 problems. It's probably, I'm going to include 1 problem that has to do with the reduction of resistors, mainly, and 1 problem that has to do with finding currents and voltages. So it's going to be two problems. It's not going to be the. Yeah, I'm gonna upload it. I'm gonna upload it today. I already have it ready, but I need to scan it. Okay, I'm gonna jump over to the next slide. Let's look at this example. We have 3 inductors that are in series, okay? And we want to find the total inductance. Again, this is relatively simply done because we know that they're going to add up, but I just want to do the procedure. I want to draw the circuit. So first off, we're going to have 3 inductors. Okay, so let's draw this quickly. So we've got 3 inductors, 1, 2, 3, and so the inductors are going to be these little loops, L1, L2, and L3, and so L1 is going to be equal to 10. Oh, by the way, remember the multipliers that we're going to be using different types of multipliers for different types of values. So I noticed that some of you guys asked me in the homework task about the K. It's a 10K or 2K. K is kilo ohms. Usually when we're talking, remember this, when we were talking about capacitance values were in the micros, nanos. Resistance values are higher. They're going to be normal, kilo, mega, etc. Inductance values are going to be in the smaller values. So it's common to have a micro, the H is Henry. Remember, the units are Henrys. A micro Henry, a millihenry, I'm sorry, a micro Henry. It's not common for us to have large values. I'm going to just turn this just as a reference into 10 times 10 to the minus 3 Henrys. L2 is going to be 40 millihenries. So this is going to be 40 times 10 to the minus 3 Henrys, and L3 is going to be 50 millihenries, which is going to be 50 times 10 to the minus 3 Henrys. So the equivalent or total, I'm going to call it LEQ. I'm going to call it LEQ, but we could call it L total or something like that. The total is going to be L1 plus L2 plus L3. So the equivalent is going to be 10 times 10 to the minus 3 Henrys plus 40 times 10 to the minus 3 Henrys plus 50 times 10 to the minus 3 Henrys. In this particular case, because we're just talking about equivalent inductance, We can turn it all into Henrys, or we can leave it in millihenries, as long as all of them are in the same range. We can do it. We can do it that way. So the equivalent here is going to be 10 times 40 times 50. This is going to be 100 times 10 to the minus 3 henries, which would be equivalent to 100 millihenries, and that would be the equivalent. That would be the equivalent inductance. Again, it's not going to be a topic of this course to go more deep into this. Actually, when we get to industrial electronics, we're going to hit the ground running because we already saw part of this. And the next thing we're going to do, we're not going to do it now, is notice that I'm not connecting a power supply. Yes.
They would be Henry's.
Sí.
This would be Henry's, 100 times 10 and this is the millihenries. It's just to represent both. So we haven't connected a power supply here, and we're not going to do it right now for the topics of this course. But the next thing that we're gonna see in industrial electronics is what happens if I connect a power supply to this and how it behaves. And then the next is what happens if I have a circuit that has resistors, capacitors, and inductors combined with a power source. How does it behave? And we're going to see some interesting behaviors there that apply directly to circuit to circuit applications.
Professor, in the,
Yes.
in the exam, like you like 10 times 10 to the minus 3, which is for 10 megahertz.
Henry's. Henry's. Yeah, it's fine. I'm just doing it this way just to represent or for us to understand the multipliers, but as long as they are all in the same units and you respect that and put it in the end result, it's correct. Same thing if I give you for this exam, if I give you a circuit with resistors and all of them say they're kilo ohms, you can do the whole analysis with that and just put that the result is kilo ohms. Okay.
So one question, Henry, is it spelled with an I or what?
Why? Henry, like Henry, like it's, I don't remember the physicists whose name is after that, but it's Henry, like a normal name, Henry. Maybe. Henry could also be French. Could be French or British. Okay. Questions with this? Can I jump on to the next one? Okay. This is going to be in the PowerPoint with the solution. Yes. Let's finish up and we're going to do some housekeeping because that was one of the questions I wanted to ask you guys. So let's ask that at the end. We're going to do some housekeeping and we want to decide that ideally today. Okay, so inductors in parallel behave the same as resistors in parallel. And how do resistors in parallel behave? Well, they behave like the reciprocal law. Yes. The inverse of the reciprocal. So 1 divided by the total or equivalent. Remember that I'm using total and equivalent as same thing. The total inductance is going to be the sum of the reciprocal of the sum of the reciprocal, same as in resistance. Why? Because again, inductors are based on current, and current is divided when we have a parallel array or circuit, and so that's why it follows the same principle. Okay, let me know when I can jump to the next one.
Oh no, it's an L.
And which one?
No, inductance is
It's usually represented with an L. Why?
No,
I don't know.
yes, it's buena, just a capital.
I think one of the reasons might be that because I is current, but
then why is I current?
no, we mentioned that. I don't know why V is voltage, that's direct, R is resistance, C is capacitance. I'm not sure why I is current.
Why did they break the
And
rule?
L is inductor.
You mean a different language current starts with an I?
I'm not sure, but maybe it might have to do with that, or maybe it might have to do with different languages. Ampere is, I think he's French, so I don't know if they say it's courant or say something. I have no idea. So, oh, in this case, we're really not analyzing the current right now, but if we had a voltage source, the current would be divided. Remember that whenever we have a circuit in parallel, the current is divided. Okay, but right now we're not connecting any power supply. In the other one, the current isn't divided, the current is the same.
We know the reason.
We know the reason why, because in French, current is, they say it as an
Intensity, like intensity.
yeah, intensity of current.
Oh, they use the I, okay, which is, it's the intense, oh, okay, okay. And the L, Google the L. Intensité.
Okay, why?
Intensité of current. I'm gonna jump to an example. Okay. Oh. Okay, so we'll do a quick example of inductors in parallel.
Because, Heinrich Lenz.
Oh, it's Lenz. Yeah. Oh, okay. So because of Lenz's law, instead of calling it, oh, okay. No, we were just talking about here, why is current called is identified with an I, and why are inductors identified with an L? So the inductors come out of Lenz's law, and Lenz was called Henry. So the I is because Ampere is French, and apparently instead of calling it current, they talk about intensité. So it's intensity of current, so that's where the I comes from, because Ampere is French. So
Professor, the current is that.
oh, well, right now, just a thing I forgot to mention. These are just over here. Don't focus so much on these. These are just explanations as to how we get to this. We're not going to be using these expressions right now. We're just focusing on the total inductance. That's just kind of the explanation there. So we need more Mexican scientists and so we can call things. Well, CH. There's a lot of things in Spanish that start with CH, so things can be called.
Oh, we should make our own space agency and call it NASA.
Masa? Yeah, yeah. The units could be the CHs. Because of chimichanga, obviously. Chicharrones, churros. Think about all the things that start with CH and chimichanga, churra, comida china. Yes. I was gonna address that. How many people here like? How many people here like capirotada? Capirotada runs in my family. We always make it. There's actually a recipe that I know how to make capirotada. So I've been eating capirotada since I was a child. Capirotada, tongue, tripitas, kidneys, a lot of things that. Yeah, little like kidneys from chickens and all that. They are yummy. They're really yummy. No, not in the capirotada. No, separate. No.
Salty one, the savory one. A savory capirotada.
No, but actually, of those of you who have tasted capirotada, and not if you like it or not, but have you tasted the capirotada that's salty? There's capirotada that has onion, that has tomato combined with the sweet one. That's more in the center of Mexico. It doesn't, I've tasted it. It isn't as weird as you would think, but it's an acquired taste because it's salty with sweet. So there's these capirotas. I know they put onions in it, and I think they put tomato in it as well. Uh-huh. Fruits and vegetables, yeah, yeah. That's more of a recipe, more. You didn't like it. Yeah. It's an acquired taste as well. Okay, so, okay, everybody over here. So in this case, the inductors are in parallel, so the equivalent or total inductance is going to be the reciprocal of the sum of the reciprocals. All of this elevated to the -1, so the equivalent or total inductance is going to be 1 divided by 60 times 10 to the -3 times 120 times 10 to the -3 plus 75 times 10 to the -3 henries. This to the -1, and that's going to be the total or equivalent. Please, somebody help me out with that calculation. Oh, that's just a, okay. Yeah, that's just to explain that. Okay, remember that an inductor is a coil, right? So it's a magnet. So I'm looking at the magnet by itself, right? But let's say that I have 3 of them and I connect them. Because I'm connecting parts that have cables or wires in them, there could be a mini magnet that's created by the connections. That's something very negligible. You don't, unless it's something very specific, you need to consider it in the analysis. So that's just kind of like a default, saying there's no mutual inductance, meaning the connections aren't generating another magnet that you need to consider. It's similar to the problems that have to do with electrical circuits. If you remember, some problems might say there's a 10-volt power supply that doesn't have an internal resistance. That just means that you don't need to consider that in the analysis. Okay? Any connection where we have a wire where current is going through it can potentially be an inductor. So it's just, you don't need to take that into account. Can somebody do that calculation, please? So. Yeah, cheese, apple. The nuts are really.
Teacher, how many we should make a class that everybody brings something?
That would be wonderful. Let me say this to you guys. Part of the philosophy that I just mentioned, I forgot to put something there that's related to number 3, that it's very important to have things to look forward to. So let's do this. If everything goes well, should be with you guys in industrial electronics next semester. Let's plan for a food day where we can bring a little taste of food that we've created for everybody. And that would be something for me to look forward to. So let's do that. Yeah, no, that's what I mean. Making. I can do either capirotada or I can do paella. Paella is a little bit more difficult, but yeah.
I can make a cheesecake.
Cheesecake is yummy. I know that Iskra, you can make good cookies and bakery. Okay, does somebody have the value of the result, please? Okay. Okay. 26.08. This would be Ajá.
Que la-
1, 2, 3, meters.
I got. Yeah, like a little increase, right?
Yeah. Either of those would be a, I'm assuming that the calculation is correct, but please,
I got the same.
perfect,
And
perfect.
it's always correct.
The Enya rule.
Did you miss her?
Yes, of course,
I miss her.
of course. Okay. Okay, let's finish up with this, questions with this one. Okay, these are all gonna be in the PowerPoint and they're in the video. So the same thing happens with, the same thing happens when I combine them. So if I combine parallel and series, I can create different arrays and the principles are still the same, okay? So this is kind of a practice exercise that has to do with the next exam, because if I substitute these for resistors, the analysis is going to be exactly the same. I'm going to jump over because the same is here, okay? Let me jump back so you can write it down.
Es que ni siquiera. No. Esto es 1/50.
Siento que al final no se va a hacer bien que la haga.
Hey,
Porque no va a hacer los trabajos.
Sí, va a ser.
eso que tiene que ver.
O sea, me gustaría ir porque estaríamos viendo todo. Ajá. Yo fui a la no me gradué. Fui muy
Okay, entonces, es 27. So, es 27. Okay, 27.
Ni le digas a la estrella.
A nadie le salió que oye. Y no lo niego.
L, 5, 6, 7, 7, and then plus 20. Entonces, 47. L, 4.
¿Dónde? Acabo de salir. ¿Eh?
Así es,
Oh, teacher, I have to play. You can eat at.
Yes.
Yeah.
Yeah. My wife's, it's her favorite food, so we eat it a lot.
Yes, I
Yeah.
love them.
porque
Quiero hacer
No, nadie está Estamos en eso. ¿Por qué? Te lo doy ahorita mismo. Ah, neta.
Es que te dan 20 segundos. ¿No los tienes ustedes? Sí, ya tengo los 20. No, tengo.
Yo cero. Papá me va a poner en la casa.
¿Cómo se le vendió? A un tío.
Ay, la verdad es que yo sí fuera mi papá.
Okay, everybody over here then. Okay, so, I'm just gonna walk through the steps here. Again, this is very similar to the ones we've been seeing with, with resistors, so let's keep the volume down, please, you guys. So first, I'm gonna mark them. I'm gonna do it the same way we did the other one. So this combination here is in series, so that would create the following circuit. Those are dad jokes. So L67 is going to be that series combination, which is going to be L6 plus L7. I'm gonna leave it in Henry's just to make it quicker. This is gonna be 140, correct? And so the next two are going to be in parallel. So L1. Yeah. Yeah, it can be annoying.
For people who don't know how to draw,
L567 is going to be 1 divided by L5 plus 1 divided by 67 to the -1. Please give me that value.
Like the first one, it was 27.
Give me a moment here. And
It's the 50 plus.
No, no.
No. So yes, the 50, yeah, I got 27.
okay, so please do this calculation and validate it.
Please, okay.
I got 36.84.
Seguro está. Because my final result was 190 over 7. And then estoy mal yo. One over.
Plus 1.
Only 567, I got 36.84. Yes, me too.
Okay.
Estaba bien, porque
No estabas bien, Fran.
yo soy
Those two.
Okay. Okay, so please let's lower the volume. No, so how much was this one?
36.84.
36.8 millihenries. And over this is going to be in series. So L4567 is going to be L4 plus L 567, which is going to be L4 is 20 millihenries plus 36.8 millihenries. This is going to be equal to 56.8 millihenries. Okay. And the next circuit, we're going to have these two in parallel. So that means we're going to have L1, L2, and this one is going to be L3, 4, 5, 6, 7, which is basically 1 divided by L3 plus 1 divided by L4, 5, 6, 7 to the minus 1. This is going to be equal to 1 divided by 30 millihenries plus 1 divided by 56.8 millihenries. Please give me the value of this one.
I got
19.6 millihenries. Okay. And these two here are going to be in series. No, they're not in parallel yet. I'm going to do this over here in the bottom. I'm going to make these a little bit smaller so everything fits. Two, 3, 4, 5, 6, 7. That's just going to be adding them up. L2 plus L3, 4, 5, 6, 7. It's going to be L2, which is 40 millihenries plus 19.6 millihenries. That's going to be equal to 59.6 millihenries. And lastly, these two are going to be in parallel, correct? And this is going to give us the total inductance, which is going to be L1, 2, 3, 4, 5, 6, 7, which is going to be 1 divided by L1 plus 1 divided by L2, 3, 4, 5, 6, 7. To the minus 1. And this is going to be equal to 1 divided by 1 divided by 20 plus 1 divided by the 59.6, all of this to the minus 1, and this would give us the total result, which would be the equivalent resistance. It's equal to L1, 2, 3, 4, 5, 6, 7. And can somebody give me that value, please? 14.97 millihenries. And this would be the final result. And just to indicate the sequence, so we're going from here to here, then we're going from here to here, then we went from here to here, from here to here, from here to here, and finally from here to here. Okay. Okay, questions with this one? Okay, these are, I'm gonna update the PowerPoint. These are gonna be there. This is gonna be included in the updated PowerPoint and the video as well.
But in the last one, signal,
Yes.
those, the L1 and the L2, 3, blah, 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 it's parallel and then what?
Here. So this is the parallel that goes here, and this is the last. So
okay,
the solution to this is the final solution.
And it's in series.
It's in parallel. So no, this is the last one. We don't, it's not connected to anything, it's by itself, and this would be the solution. So reducing the parallel gives us the total inductance.
As a parallel.
How do you know this one? Well, this is a parallel because we'll get a parallel. This one clear, Lisa? The previous one?
Yeah.
And you know you're done, Lisa, or you found the last result when you were only left with one?
It's just that I drawing them different.
You're probably drawing them better.
If we don't draw them, there's no problem.
That's a good question. Yes, that's a very good question. I'm gonna answer it this way. If you're gonna do for the exam or for exercises, try to do the procedure in a way that I can follow it.
Oh,
So-
yes, each order.
Yeah, you don't necessarily have to draw all of them, but just kind of indicate what is what. So if I need to review it and you made a mistake, I can check in which part.
It's because, for example, like L4 plus L567, and I put dash series, like this,
Oh.
adding this.
You indicate
this
which
is a
one.
series, and
Okay.
then because I think I get more confused with the drawing.
Yeah, as long as it's an ordered procedure that I can follow, it's fine.
Okay.
Yes.
It's without sugar, and I always make the steps.
Oh,
They have, like,
send me that, because the thing is, all the sugars have been eliminated, so I can't eat, I need to see what types of,
I also, well, I don't.
Sugar.
It was-
oh, well, send me those because the bad thing about being on a diet is that I have to be on a diet, but my daughter was like, we were telling her, so Sarah, we're gonna start being fit. And she was like, no, she literally said, I'm going to leave this family because she eats pizza 2 out of 3 days a week.
Quiero mi pizza.
And so she's like, daddy's gonna be fit, but don't make me be fit. So yeah. Yeah, so at least I need to find alternatives that can be good for the whole family.
You can eat pizza from the floor.
It sounds interesting. I've eaten vegetarian pizza and it's really good, but I don't remember cauliflower being on it.
Like, but it's not like the process cauliflower.
Oh, that's for the flour or something like that?
Cauliflower, the crust is made
Oh, is it good?
Professor, I made this with oat milk with NX, and then I just mix it and I put it in
The pan? It's good as well?
And I just added a little bit of cheese and I like a little bit of cheese and jam.
Jam. That's what-
Tomato sauce.
Tomato sauce. Oh,
What?
ham.
Ham.
Okay.
Anyway,
Jamón.